Yes, good evening. Last day we have discussed topic name is.
Voice not clear, right? Hello?
Yes, I'm audible.
No, sir, the voice is very low. Your voice is very low.
Yes, now check. Recheck.
Yes, now. Yes, sir. Now it's fine, sir.
Yes.
Now it's fine.
Then last day we have topic name is.
Chemical kinetics was over, sir. Now you told me to
Yes.
start a new topic.
Yes. New topic
With
is.
the thermodynamics.
Yes. Yes. Let me start. Basic principle of thermodynamics. What the basic principle of thermodynamics?
Just 1 second, sir. There is network issue.
Yes, no problem.
Thermo, 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 heat.
Yes.
We will study the change in the heat on the system and how it affects the surrounding. So basically, this is the basic study that we do. How heat is, for example, heat is converted into work and work is converted into heat. So this is the basic funda behind it.
Yes. What is system? And what is system and how many types of system thermodynamics?
Yes, sir. The system is while, for example, let me give you an example. For example, we are working, and we are working. For example, we are heating a glass of water. So for us, it is system, and all the other part apart from that is the surrounding. So system plus surroundings will be equal to universe. So systems are of three types. One is open system, both energy and matter can flow. Second is the closed system. Closed system we have open system, and the other one is closed system. Closed system is heat. Heat could both heat and matter could not flow, I guess, to be precise.
Yes. Closed, open, and isolated. Yes. What the example of each one?
Sir, open is the open system, sir. For example, open, closed, and isolated. The open system is iso.
Boiling of water.
For, yes, sir.
Boiling of water.
Huh, yes, sir. Boiling of water, for example, when you take, sir, the water vapor goes in in the surroundings easily. So both matter and energy are being exchanged. So, for example, sir, the other one flow system, when you take, sir, for example, heat, matter would not flow, but heat would flow. For example, sir, uh, mm, mm, thermal flask, for example, you take, sir,
Yes.
the heat
Thermos.
would not flow. Yes, sir, thermal flask, for example, heat would not flow, sir. It would remain same, but yeah, if you matter also, sir, remains constant, I would say. So it is the example of isolated, I guess.
Yes.
Both
Isolated
energy
thermos
and
flask.
matter.
Yes.
Yes, sir.
Closed system is gas in
And
body या human body.
yes, sir.
Isolated system is thermos flask. Closed system is gas in balloon या human body.
Yes, sir.
Open system is boiling of water. Yes, examples.
Yes, sir. Okay, sir.
Next is what the difference between other system is like homogeneous and heterogeneous system in thermodynamics.
Homogeneous system and heterogeneous system.
In thermodynamics.
Mm, Yes, sir. As per the word homo means similar. So a system which is composed of, for example, system, I would say one matter. I would say, for example, in one phase, I would say solid or liquid or gas in one phase. Heterogeneous, I would say, as a hetero means mixture of many. So mixture of many, I would say, mixture of many components. I would systems. I would say in three phases: solid, liquid, or gas. So what do you say, sir? Interview, if you don't know the thing, so do we have to do a calculated guess, or do we, on a safer side, just say no to it? No to it if you don't know any answer.
Only basic
Don't tell
idea.
wrong answer.
Yes. Yes, paper work या whiteboard.
Okay. No, sir. I'm asking if you don't, if a candidate doesn't know the correct answer, right? If we have to do a calculated guess, do we have to tell the answer or simply say no? What would be a better choice, sir? And then interview.
It's a expression of them. Yes, like to
Hmm.
expression. They will not
Okay.
say you are right, you are wrong. Yes,
Okay.
only expression.
Okay.
We feel that expression of them. Yes.
Okay.
Yeah, let's move on thermodynamics. The basic part is what the difference between macro and microscopic properties? What the main application? Any example?
Macroscopic and microscopic property.
Yes.
Um, Sir, based on calculated gas, macroscopic properties are the properties which are on a larger scale, and micro properties are on a smaller scale, I would say. But the exactly the difference I won't be able to give you. For example, I would say that for microscopic, temperature, for example, properties like thermal temperature, pressure, and these kind of properties would come into microscopic. And macro, I would say, I don't microscopic, for example, weight and all would come into that.
Pressure, volume, temperature, density,
Yes, sir.
macro.
These would come into okay,
Large
macro.
number of particles is macro. Micro is small number of particles is micro. Mass, bond angle, bond length.
Okay, sir.
Next is what the difference between extensive and intensive property in thermodynamics. What the uses?
Yes, sir. Sir, yes, sir. Sir, basic difference is intensive property is independent on the amount of matter. Another properties that which don't not depend on the amount of matter. For example, temperature is there, pressure is there. They don't depend on the amount of matter. If the property depends on the amount of matter, it would be called as extensive. For example, weight is there, which is expressed in kilogram, and there are many more, sir. For example, uh, 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 kilogram is there, length is there, sir. Length also depend on it. Weight and length and
Examples?
many more.
Example intensive, extensive.
So, what's
Example of
sir,
intensive.
extensive. Sir, example of intensive you are talking about.
Yes, intensive example is
Sir, for example, temperature, pressure, and standard E naught cell, I would say, standard
pressure,
electrode
yes.
potential. Uh,
Pressure, volume point, melting point. Yes.
if you if you take the if you take the ratio of two intensive property, it will come out to be two extensive property. It will come out to be intensive property.
Yes, extensive property example.
Sir, length is there, weight is there, kilogram, which is present in kilogram, and I would
Yes,
say,
mass
sir,
energy.
ma-
Yes, mass energy heat. Yes. Yeah, next move on. First part of thermodynamics is basic isothermal process. What is isothermal process in thermodynamics? What is the main application?
sir, isothermal. Okay. So the isothermal processes. iso means same and thermal means heat. So when any process takes place at a particular temperature, at the same temperature, it is called as isothermal. It is usually of two types, reversible and irreversible. So this is the isothermal process, sir. Um,
And isobaric,
uh,
isochoric.
Sir, isobaric is when the process takes place at a particular pressure, at a same pressure. It is called as isobaric, and isochoric is when the reaction or the process takes place at a constant volume. So at a constant temperature, it is isothermal. At a constant pressure, it is isobaric. At constant volume, it is isochoric.
Yes. Next is adiabatic process. What is adiabatic process?
The adiabatic process is when the heat is constant. So heat doesn't exchange. So dq is equal to zero for an adiabatic process.
Yes. Cyclic process. What is cyclic process?
The cyclic process is, for example, for a process A goes to B. So and if the process comes back to B to A, so for that the process is uh, cyclic cyclic process is when, for example, A is in equilibrium with B. So A goes to B and B comes to A. So it is an example for of this cyclic process.
Yes. What the difference between reversible and irreversible process in thermodynamics? What the uses?
Yes, sir. Sir, the reversible process is, for example, every at a at a fraction of time, at a fraction of, for example, reversible processes, when there is when every process is reversible at every point in a fraction of second, it is usually reversible, sir. It can come back, for example, this thing. Um, um, in irreversible process, the process cannot be reversed further, cannot be reversed. So it is a reversible process. For example, the expansion of a gas at a reversible process. So at every second, at every fraction of second, there will be a change which is infinitely small. So you cannot see by naked eye. So for a reversible process, you just open a piston, for example, of a gas. So gas will occupy the room. Is an example of a reversible process.
Yes. Good. Next, move on work. What is work? And what the difference between work done on the system, work done by the system in thermodynamics?
Um, Sir, work is, sir, when you, for example, when you provide heat to the system, it has usually two options: to increase the internal energy or to do a work. In for gaseous system, dw mathematically we usually express dw is equal to minus p external dv for a particular gas work. Work, how do we express it? So mathematically we usually express work like this only, sir. And what were the other questions, sir? What is the difference between work and?
Work done on the system, work done by the system.
Sir, work done by the system is, for example, the work done by the system is usually taken as negative. It comes out to be negative, and work done on the system is usually positive. So how we express is, for example, you just compress a piston. For example, and there is a container, and you just put inside a piston. There's a gas inside, and you just put the work done on the system. You are just pressing it, so it is work done on the system. That is by you. But when you remove your hands and other application, and when you just set aside and just see, so piston will automatically come up. uh, so when the piston is coming up, it is usually work done by the system, and it is usually comes out to be negative. So this is the basic difference between on and by. For example, expansion of a gas is usually taken as by the system, and when you compress it, it is on.
Yes, good. What the difference between PV work and non-PV work? What the difference?
PV work.
Yes, pressure volume work.
The PV work is, for example, work is equal to minus P external dV, right? When there is an external pressure also, when there is initial and final volume, it is uh, usually said to be PV work, as work can be easily said in terms of P in pressure and volume. Non PV work, sir, I'm not able to. If you, uh, I'm not able to tell you that. I will read this after that.
Your next question is state function and path function. What the difference between state function and path function in thermodynamics? What the main application?
Sir, state function is when the state function is when your work is depend when your process is depend only on the initial and the final point and not on the path which is taken by your process. Path function is it when the work or the process depends on the path which is taken by the system and not on the initial and the final point. This is the basic difference between the state function and path function.
Yes, what the
For
example?
a
State function, path function.
mm, for example, for a state function, if you are taking it, for example, Carnot engine is also an example of state function. Uh, and path function, for example, if path function can be any example. For example, you just open up a piston. So you just open up a piston, for example, you take any initial volume. So there are various ways how you can open it. For example, adiabatic, you can go by work can be done. For example, work can be done as adiabatically or isothermally. So there are various pathways how the work is done.
Yes, path function is example Q and W. Yes, heat and work.
So,
State function is example enthalpy, energy, gas
hmm,
free energy, entropy. These are the example of path
yes,
function.
yes.
Yeah, next move on the zero law of thermodynamics. What the main application of zero law of thermodynamics?
Yes, the zero law of thermodynamics is, for example, A is the equilibrium with B, and for example, B is the equilibrium. A system B is the equilibrium in equilibrium with C. So it usually sells on the basis two conditions. A will be also will be in equilibrium with C. So this is basically the zero law of this thing, thermodynamics. So we generally study this.
Any example of zero law of thermodynamics?
Any example?
Any limitation, drawback?
Uh, Sorry, sir, I'm not able to tell you.
Here, next move on first law of thermodynamics.
Yes, sir.
What the main
The first
application
law
of
of thermodynamics, sir, first law of thermodynamics tell usually that energy cannot be created nor be destroyed. It can only be transformed from one energy into another. It is usually a first law of thermodynamics.
yes, example of first law of thermodynamics?
Energy can be transformed. For example, sir, For example, sir, you provide energy to a system, right? You provide heat to a system, so it can increase entropy of a of the system. So energy, we provide heat, it increases the entropy, the internal energy. It increases the entropy. Energy is transformed from one to into another. So it may increase the entropy of the system also. This is an example how energy is being converted from one form to another. For example, sir, in real cases, when you heat or boil, when you, for example, in thermal power plant, for example, when you are heating it, sir, the water boil will go, and it will, it will let the turbines, rotate, and will produce mechanical energy. So how energy is being transformed one form to another on practical basis.
Yes. Any limitation of first law thermodynamics?
And so the limitation is does not tell you about the spontaneity of the reaction, and it does not tell you about the direction of the in which the reaction proceeds. So there are basically two limitations.
Yes. Next, move on second law of thermodynamics. What are the main application of second law of thermodynamics?
So second law of thermodynamics is still tells you about the spontaneity of a reaction. The spontaneity, heat is converted into work, and work is converted into heat. Heat is converted into. It tells you about the spontaneity. How is heat when you provide heat to the system? It will turn out it the system produce it, the system will do work, and vice versa will not happen, I guess. So it will tell you about the spontaneity of the reaction.
Yes, what is entropy?
uh, entropy entropy is the measure of randomness of the system. For example, randomness of the randomness inside, what is the randomness present in the system. For example, at 30 degrees Celsius, there are certain particles present in a cube. But when you increase when you give heat to the system, when you heat it, so the speed of the particles would increase, and there will be more collisions. So in short, we usually tell the randomness increases, so the entropy also increases.
What's the difference between entropy, absolute entropy, residual entropy? What are the differences?
Absolute and residual entropy. Uh, I don't know the exact reason, but on the basis of calculated, yes, I would say, sir, absolute entropy is the entropy uh, that we usually measure at 0 Kelvin, may or may not be come out to be zero. Residual entropy is the entropy which is based on the orientation, and its formula might be equal to SB ln KW. It depends on the orientation.
Yes. What is Newton's law in thermodynamics? Newton's law. What is the main application of Newton's law?
The
Protons.
Newton's laws are is the measure of entropy, uh, is equal to 10.5 into R. The formula is entropy is equal to 10.5 into R. So it usually gives entropy, the formula which is the formula helps to calculate the entropy.
Yes. Del S is equal to del H upon T. Newton's law. Yes. Entropy is equal to enthalpy upon temperature. What's the difference between spontaneous and non-spontaneous process in thermodynamics?
Spontaneous processes are, for example, once you initiate the reaction will go on, proceeds with itself, with the no interference required further. For example, sir, you burn a candle, right? When you just torch a candle, it will light on its own till it's end. Non-spontaneous processor, heat generally at regular intervals or irregular intervals you have to provide energy to the system. So these are basically non-spontaneous processes. For example, for mechanical work, you have to provide energy in the form of coal or fuel, petrol, gas. These are all the basis of non-spontaneous gas.
Yes, good. Next, move on third law of thermodynamics.
The third law, third law of thermodynamics tells the entropy at 0 Kelvin is zero, sir, usually. So third law of thermodynamics still uses of an entropy of an absolute crystalline solid at 0 Kelvin is zero. It usually tells us.
Yes, what is the difference between entropy and entropy of mixing? One question left from second law of thermodynamics.
Entropy and entropy of mixing. The entropy of mixing, I can tell you, for example, when you study two or more gases in a system. So when two gases mix, so sir, we study the entropy of mixing, how the randomness, uh, is there. For example, delta H is equal to minus uh, x ln x is the formula is minus x ln x is the formula, sir. And entropy for a system we can study, sir, any entropy, the randomness of the system is simply how the gases behave in a mixture. It is usually an entropy.
Yes, any limitation of second law, third law of thermodynamics? Any limitations?
Limitation would be at 0 Kelvin, the absolute entropy is usually zero because entropy is also calculated on the basis of orientation. And drawback of third law of thermodynamics.
Yes. The next move on Joule-Thomson effect and Joule-Thomson coefficient. What the difference?
The Joule-Thomson coefficient, for example, is dT upon my dt at constant enthalpy is equal to mathematically is equal to minus 1 by c.
Yes.
So this is the formula mathematically of Joule-Thomson coefficient. we study any gas, for example, the change in temperature with respect to pressure at constant enthalpy is usually Joule-Thomson coefficient. It is its applicable its application in today's life is in air condition that we use.
Yes. What the value of Joule-Thomson coefficient for ideal gas and real gas?
Sir, for ideal gas, the Joule-Thomson coefficient it will be equal to 0, sir, for an ideal.
Yes, ideal gas is 0. Yes. Real gas?
For real gas, sir, I'm not able to
Real gas mu J is equal to positive value. Very high pressure and high temperature. So what will be the value of real gas for Joule-Thomson coefficient?
So for high value of both the temperature and pressure, sir, it will for high values, high temperature and pressure, Thomson coefficient would be equal to 1.
Very high pressure value is negative. Real
Yes,
gases.
sir. Yes.
Joule-Thomson coefficient is ideal gas value mu J is equal to 0. Always 0. Why?
Yes, sir.
High pressure, high temperature. What the reason?
Sir, because the for an ideal gas, the difference in the difference in the temperature would be equal to 0. So at constant enthalpy, at constant enthalpy, constant temperature is usually 0 for an ideal.
Yes, you look them the point of change. Yes. Next is what is inversion temperature? What the main application of inversion temperature in thermodynamics? What the formula?
Sir, in sir, the inversion temperature is the is the temperature at which an ideal gas at a real gas behaves like an ideal gas, and the temperature for an by RP temperature for an inversion.
Yes. Ti is equal to 2A upon RB. Yeah, next move on. Heat engine. What is heat engine? What the main application of heat engine?
Main application for
Yes.
sir, for example, the heat engine is when you provide energy to the system. When you provide heat to the system, for example, what is the amount of work that your system will do? It is basically an heat engine, and its application, for example, in its application is simply a Carnot engine, for example, you see. So how your system is reacted when your input is heat. This is the basic fundamental.
And what the formula of efficiency of a heat engine?
Sir, efficiency is equal to 1 minus T2 by T1. And sir, the temperature, the above one, the 1 minus T2 over T1, T1 would be higher temperature and T2 would be a lower temperature. Efficiency is generally less than 1 or 100%.
Yes, eta is equal to W upon Q. Yes, no?
Oh,
E2 is like
eta is equal to
upon
minus
Q.
W upon Q.
Yes.
Eta is equal to minus W upon Q.
The next move on Maxwell relations. What the main application of Maxwell relation in thermodynamics? And Carnot cycle also left.
The Maxwell relation is uh, Maxwell relation generally gives you four equations. Equations, for example, enthalpy, internal energy, Gibbs Helmholtz energy, uh, and uh, and they help in deriving the properties for the system, sir, Maxwell. And they are so named Maxwell equation because the scientist's name was Maxwell. And and for example, their application in this Carnot engine is a Carnot engine is a cyclic process. So for a cyclic process, dq for a cyclic application, for example, in terms of these four ds, du, da, dg, in terms of ds, entropy, pressure, volume, and temperature. These Maxwell equations usually tell you. Do we have to, sir, derive the Maxwell equation also? Four equations and equations.
Yes, next day drive and a Carnot cycle only applications. Next day we will discuss.
The
Carnot cycle applications.
Carnot cycle,
Yes.
the Carnot cycle application is generally the for example, the application is usually the this railway this engine that we use in older times. The engine, so we usually put coal in that. So it was basically a heat engine that we used in ancient times. This was the major application of course.
Yes. Good. What the difference between what the uses of Carnot cycle? Uses, drawback, limitation, Carnot cycle.